This lesson we'll take a look at mass spring systems. So a mass spring system is any time you have a mass attached to a spring, and we're going to consider only special springs called ideal springs. But we're going to look at what happens and how do we describe this oscillation. So in lab, what you guys did was you applied a force to the spring and you measured how far it stretched. And I think you found that the displacement, the stretch, was directly proportional to the force. So your math model looks something like this. On the y-axis, you have the displacement. On the x-axis, you have the force. So we're going to think about it just slightly differently. What we did is we applied a force and measured the stretch. But you could think about an experiment where you stretched it and measured the force that it took to do the same job. So it's basically exactly what we did, except switching the axes. So in a slightly different experiment, we would control the distance we stretch it. So you would stretch it a fixed distance, and you would measure how much force it applied. So this would require a force sensor, which we could do. But in either case, whether you do it this way or this way, you find that there's a direct relationship between the force that the spring exerts and the distance it stretches. And this relationship is called Hooke's law, named after Robert Hooke. So in this case, the experiment we didn't do, but if I plot delta x in meters on the x-axis and the force on the y-axis, I can say the force equals the slope times delta x. And so in your case, if you take 1 over this slope, you'll get this slope. Because if you switch x and y, the slope is the reciprocal. So this relationship is what we call Hooke's law. And it looks like this. So the force exerted by a spring is proportional to the distance the spring has been stretched or compressed. We didn't do that, but you can also compress a spring, and that requires a force. So how much force you need is proportional to the distance you wish to stretch it. The constant of proportionality is a number we are going to call the spring constant. It represents the stiffness of the spring. A large spring constant means you need a big force to stretch the spring. And a small spring constant means you just need a small force to stretch the spring. So the K, the spring constant, is also thought of as the stiffness of the spring. The bigger K is, the greater the stiffness of the spring. So F is the force, and this is the force the spring exerts. And there's a minus sign here because whichever way you pull it, the spring exerts a force in the opposite direction. So if I pull it to the right, if delta x is to the right, then the force that the spring exerts is to the left. So that's why there's a negative here, okay? So we call that Hooke's law, and it's just a simple relationship between the force and the displacement. On your AP reference sheet, it's written slightly different. If you find your AP reference sheet and you look down there on the left-hand side, you'll see the equation looks like this. What they actually do is they handle the negative by just putting absolute values. So in the equation they give you, it's the magnitude of the spring's force is equal to K times the magnitude of the displacement, okay? But you also just need to know that whichever way you displace it, the spring exerts an opposing force. All right, so that's what we call Hooke's law. Now, let's just quickly review some big ideas. If I plot the velocity versus time, the area under the graph tells me something important. It tells me the displacement, how far an object has moved. If I plot the force versus the time that the force acts, the area under the curve tells me something important. It tells me the impulse, which is how much the momentum changes. And the third one you have to know for the AP exam is that if you plot the force versus the displacement, the area under the graph tells you the work done or the energy transferred. And this is the one we're going to use right now. So if we plot force versus displacement, the area under the graph is the energy transferred from one form to another. Okay? All right, so if I wish to stretch a spring, I have to apply a force. And the greater distance that I wish to stretch it, the bigger the force becomes. So if I were to make a plot of the force versus the displacement, if I want to stretch the spring all the way out to some point, let's say here, then to figure out how much work I need to do, I've got to find the area under the graph. So if I want to stretch the spring all the way to some point, I've got to find this area right here. So that's what we're going to do, okay? So here's my force versus displacement graph. I wish to stretch the spring all the way from 0 to some point delta x, okay? Now, The slope of the graph is k times delta x because Hooke's law. Now I'm ignoring the direction. I could plot this in the fourth quadrant, but it's a little hard to visualize. So I'm ignoring the direction. I'm just saying the magnitude of the force is equal to k times delta x. So if I want to find the area under the graph here, which is the work I would have to do to stretch the spring, I've got to find the area of a triangle, which is 1/2 the base times the height. In this case, the base is delta x. The height is the force, which is k times delta x. And so the area is really 1/2 times the base times the height, which I can write like this. The work is 1/2 k times delta x squared. And so that gets us to our second important equation. When you stretch a spring, you store energy in it. The energy that you store in the spring is called the elastic potential energy, and you can calculate it by taking 1/2 k times the distance you stretch the spring squared. So the elastic potential energy is proportional to the distance it's stretched squared. This is important because if I double the distance I stretch the spring, I quadruple the energy that I have stored in my spring. So using our general convention, U is potential energy. We're going to use a little elastic here to represent the energy stored in a spring or a rubber band or any media that can stretch. And that's in joules. And it turns out if you work out the units, newtons per meter times meter squared is newtons times meter, which is a joule. So it has the right units. On your AP reference sheet, it looks slightly different. It looks like this. U means potential energy, and this is the potential energy of a spring, and it's 1/2 kx squared. Okay? I'm going to use delta x because it helps us remember that what we really care about is how far it's stretched from equilibrium, which we'll talk about later. So there's a reason I'm using delta x instead of x, but maybe it's not obvious yet, and that's okay. All right, so that's how much energy is stored in a spring. That's the second equation. So this is a lecture. It's very short, but you get 3 equations on the AP reference sheet out of it. So that's the second one right there. Okay. Excuse me. In lab, you guys also asked, how does the period of the mass depend on the mass? So that little mass was bouncing up and down, and you measure the period, you measure the mass, you try to find a math model, and if you take the square root of the mass and plot that, you get a nice straight line that goes through 0, 0. So I think you can see from your experiment that the period of the mass on a spring is proportional to the square root of the mass. Later in class, we'll derive the actual equation, but it looks like this. For a mass oscillating on an ideal spring, the period is given by this, 2 pi times the square root of m over k. And this looks very similar to what you just did for the pendulum. There's some deep connections between the two, which will come out next week. So we're just going to solve problems with this today. So m is the mass, so here's sort of the annotation. T is the period, it's measured in seconds. M is the mass, it's measured in kilograms, and K is the spring constant, which is measured in newtons per meter. So if you take M divided by K, you get the period. In this case, the period is proportional to the square root of the M. So if you make M 4 times bigger, the period will double. So in order to double the period, you have to make the mass 4 times bigger because of the nature of the relationship. And then on your AP reference sheet, it looks like this. It's very similar. The period of a spring is 2 pi square root of m over k. Okay, so you're going to solve some problems with mass on spring systems. You're going to do a couple calculations with Hooke's law, a couple calculations with energy, and then a couple of calculations using this equation here. And then that'll all set us up for next week, where we will put these ideas all together and derive the theory behind what is called the simple harmonic oscillator. Okay? All right, so get going on the problem set for the second one if you're not there yet, and I should be back tomorrow. Thanks, bye.